Good. Okay, so I've tried to keep this as a topic being evidence-based macro logistics for emerging economies, but a focus on disaggregated freight flow approach. So I think the main focus must be partially on methodology and giving everybody a chance to understand, and maybe you can ask some questions. Just for those that don't know me, I thought I'd just tell you one quick slide about myself. I'm a researcher and senior lecturer at Stellenbosch University here in South Africa. I'm a part-time consultant for the World Bank, and I'm full-time employed by a group called Gain Group, and we primarily focus around freight modeling. I'm a really unique case. I've got a bachelor's degree in logistics, honors in applied maths, master's in transport economics, and a PhD in industrial engineering. And I'm still hoping one day I meet someone else that's got this quite widespread research areas like myself. I've got quite a few years in freight modeling, and I've got a fantastic team, specifically here in Cape Town. We've got quite a great team of collaborators that work in these sort of research areas. And even internationally, there's a couple of us that work together on freight modeling. So I've been very lucky in the opportunities I've got to actually have experience and allowed to work in this sort of area. So the three main areas I want to cover is on data collection approaches, the objective, and then the data collection challenges of this, and then a methodology of freight modeling itself. So I always tell people there's generally three approaches to collecting data. The most obvious one is doing a survey. You can go and ask people questions. You can see what they can tell you what's happened. We found extreme evidence that this is not reliable. There's no incentive for people to tell you what is a truthful answer. It gets completely biased towards what the answers are. If you ask someone where they move something from, if you ask someone in England and it's maybe 50, 60 kilometers outside of London, I'll bet you they're going to say London just because it's this nice, famous name of a big city, but you've lost the actual accuracy of where that freight actually came from. If you look at what we call the supply of transport, that is looking at what you can physically see, what is supplied in the economy. If you look at trucks, you can go and count them. You can factually say how many trucks there were. You don't know if it's empty, if it's full. You don't know where it's going from to. You don't know what the commodities are. You lack a lot of the underlying data behind that truck movement. If you look at what we call the demand of transport, this is the area that we find most fascinating. If you know that there's something has entered an economy, and a quick simple example is fruit. If you know fruit is grown in an agricultural producing area, and you know it's consumed by people living in a high dense city area, you really know that there's a demand for fruit, and you know there must be an interaction between points of production in an agricultural area and points of consumption where there is populations-based city areas. So the real trick we find is to triangulate all of these, to have a little bit of everything, understand information from surveys and understand from vehicles that are observed in the economy. And when I say vehicles, you should see on the slide, that includes things like rail. You can factually see rail, and you can know where other movements are, like pipelines and things. So we say triangulate these, try and use the strength of all of these approaches, but also have the gravity modeling, which accounts for, keeps all in balance, and then use things like traffic counts and vehicle counts as a sort of a form of verification. So this wider methodology has been applied all over the world. We've got experience in all of these countries and cities. We've done this on a country level like South Africa, India, Mongolia, Uzbekistan. We've also done it on a regional area, so multiple countries. So if you see the second image, top left, we've done this for sub-Saharan Africa. That's for all the countries south around like Burundi, Rwanda, and south. We are currently doing work for MENA, that's the Middle East and North African countries. So that is modeling regions. So that is including trade between countries. But we've also done it, like you see top right, on a city level, like just the highly dense city of Kolkata. And the same methodology is applied across all of these, whether it's for a city or a province or a country or even a region. So looking at the objectives and some of these challenges with getting data. Data is a big problem. Now, depends on where you are in the world. If you are in some of the first world countries, you can get amazing data. It's fantastic. You've got information and it is easy to go and get, but how valuable is it? And how are you going to do it for countries where there's nothing? So what we like to focus on is on the emerging economies. In these emerging economies, the availability of freight information is extremely low. But what is the benefit? If you're able to use it, you can have massive benefits by these places where there is low data. So let's look at some of them. If we look at some national statistics, and I love that, we look at a country and you first can go and see their Department of Transport, or you can look at their National Statistics Bureau, and many countries publish data on freight. So let's look at some. And then we look at it and think, but does this make sense? This is an example in Uzbekistan. This is the official statistics of Uzbekistan, which is done by their Committee of Statistics. So you'll see here, we've got, 8 years of great detailed data of tons. And you can see they've done a re-index. That's okay. That happens all over the world. There could be reasons why, but that's interesting. Then let's go and see. So this view here is tons. So let's call it around about that's about 1 billion tons in 2017. Now they also give for ton kilometers. Now for the ton kilometers, they're giving around about 13 billion ton kilometers. Now, if you're looking at just one of these graphs on their own, and let's say this had a little bit of like, let's say, movement to these sort of lines, this might sound great. You know, we've got great data. There's a time series. It looks good. But let's put the two together and let's give this a quick thought. If there's 1 billion tons and there's 13.6 billion ton kilometers, that means the average freight is moving only 13 kilometers. That doesn't sound logical to me. So what happens is, on face value, the data can be good, but you got to understand what's happening here. Now, one of the biggest reasons is there's things like multiple or double counts. Now, I'll touch on that just now. Much like I've just shown you the interrelation and how there's nonsensical links between tons and ton kilometers, the same thing happens if you look at things like tons and populations, tons and geographical areas, value per ton, even links between commodities, and such supply chains could be in balance or completely out of balance. If you were to go and look at the tonnage volume for a heavy dense city like London or like the main city of Delhi in India, and you were to take what is assumed to be the freight or the tons there and you divide it by the population, you might get a nonsensical answer. You might get it that each person only results in 1 kilogram, or you could get it that each person results in, let's say, 5,000 tons. But there would have to be a logical assessment of, can this data reasonably be used for any sort of form of accuracy? The much like looking at tons, if you were to go and have value per ton that is realistic, let's say you take the average value of electric goods or even the value ton of coal or something, and you compare that, if you multiply that by assumed or national statistics for volume, and you multiply tons by value, you might start getting where the freight value might be 5 times what the national GDP is. And then you start saying, but where's the problems? Which of these data sources should I believe or not believe? And things like supply chains and balance, I'll show you a slide now. So the step is always do a sanity check on any data. Before you can do any modeling, rubbish in is always going to give you the rubbish out. If I show you a supply chain view for South Africa, this is a representation of some of the main movements of domestic coal. So I've excluded export coal here. There's the main movements of domestic coal. And if you group the domestic coal with domestic iron ore and domestic manganese, you are able to influence and enhance the steel industry. So if you were to increase iron ore domestic production, increase the coal or availability and manganese, you could be able to increase steel production, thereby enabling increases in machinery and motor vehicles. But if a national government was to go and announce that there's going to be an enhancement or stimulation for the motor vehicle industry, you need to understand that you need to have the depending commodities underneath this must also be influenced. So when we look at it on a freight modeling, we need to understand for each and every commodity at each and every district. So another way of showing that is to say, let's pretend we're looking at their district number 4. And let's say we're chopping down trees and we're producing wood logs. Those wood logs might be transported to district number 15, or it could be gone down there to district 34. Now, if we've taken it to district 15, that now enables us to have other products. Now we can have wood planks and sheets can go and be produced from those wood logs at district 15. That then in turn can move from the other districts and it can become furniture or other wood products. But if you were to now suddenly want to increase the furniture production, you have to have cognizance or records of the wood planks and the wood logs. Otherwise, you can't just produce furniture out of nothing. So these sort of things need to be in balance. And many a time you can find information and they don't all sit next to each other. On the topic of the tons and ton kilometers, I like to tell everybody this example. If you consider that there's a truck coming down with 10 tons of freight coming from Zimbabwe down to Cape Town, you will see that this truck gets observed on the first corridor between the border post and a very dense city called Johannesburg. In Gauteng, that's where my mouse, if you can see over here, is that's Johannesburg. So you'll see that truck gets observed the first time. But what happens is that same truck gets observed again in the metropolitan area and on the corridor, and then it's going to be observed again in the metropolitan area of Cape Town. So what has happened in this case is that we've moved 10 tons, we've observed it 4 times, it could have been multiple times. So now what happens is someone reports that this is being 10 tons and someone else reports this is being 40 tons. So now there's a massive confusion, and that's the kind of thing that happened there in Uzbekistan, is that national statistics get reported when there's no way of understanding or removing this double count or multiple counts at each and every time. So let's look at the facts. Factually, one load was moved and it was observed multiple times. So what we want to say is ton kilometers is always the measurement that should be comparable. So as this example, if you look at this blue block, if that can represent 1 ton and you move 1 ton over a distance of 100 kilometers, that is going to be volume multiplied by distance will give you 100 ton kilometers. That is equivalent to me saying if we take 10 blocks each of a ton, so there's 10 tons, we move at a shorter distance being only 10 kilometers, you will still get 100 ton kilometers. So this is a sort of a measure of freight intensity that sadly there's less and less measurements. If I look around the world and I find logistics freight data for countries, I can much easier find tonnages than I can find ton kilometers. Now, if we look at this example I gave you from the freight movement from Zimbabwe down to Cape Town, the tons is difficult to align. But if I was to change that to ton kilometers, now it makes complete sense, because if it's a distance of around about 2,000 kilometers, 2,000 kilometers for 10 tons will give you 20,000 ton kilometers. And you could see roughly 500 ton kilometers in each metropolitan, 15,000 in this corridor. Now it makes no difference. However you want to cut up this freight movement, it could be 100 observations. The ton kilometers will always be in sync. And that would be a good goal, to try and see, can you find statistics that can be in sync or in alignment when there is a measurement of ton kilometers? Now, on this objective, what do we want to do? We want to try and create a standardized model. So what we say is, no matter how we can change any inputs and change things, it must always have a standardized output, irrespective of what we put in. We can improve it each and every time. We call it a living model. It can't just be a once-off scenario. It must be able to change. These standard outputs, we need to be able to answer questions. So we start by saying we need a geographically and sectorally disaggregated supply and demand data, and the result must be these measurements. We need to understand origins and destinations, knowing where freight comes from and goes to. We need to understand what the commodity is and how much it is and on what mode. This enables most logistics questions to be answered. So we say this is a challenge that we face, and the trick is always to be able to handle different data sources, be able to have a dynamic input, but always be able to produce standardized outputs. So we need to not only answer questions, but we want to be able to create questions. So if we start with some of these questions by saying how much was moved, that's the easy one. You can normally find information about that publicly on websites by, as I said, national statistics offices. But there's many questions. You want to know how much of what was moved. Then you want to know not only what it was moved, what the commodity, where it was moved and how. If you're able to get to this point by knowing how much of what and where is moved, you can't disaggregate below this. So what I mean is, if we were to know how much of what was moved and where, and later on someone wanted to say, but let's go and look at a modal split between road and rail, that should be an input. Unless you can capture on the input side what is road and rail, you can't easily disaggregate this. Much like if I just knew how much was moved, it's very difficult to disaggregate that into what the commodities are. You need to get to this point. Now, why I'm saying that is, if you get to this point of knowing that, you can now do, let's call building up. You can say, well, if we know how much and what was moved, where and how it was moved, I can now start saying, okay, but what was the transport cost? What is the cost to the environment? You could go and add in delays and say, what is border post delays? What was congestion? But you need to have a base to go and build from. So that's the objective, to be able to understand this last great question. Then you can build and answer so much more. Now to the interesting stuff on the methodology, which is mostly where I'm going to lose people, and I also struggle to explain it. We start by saying, let's follow grounded theory principles, whereby we say, let's learn as much as we can. We start with data collection and discovery. We then try and understand this data. There's coding, there's analysis to try and have triangulation and making sure that you've got a full grasp of this data that you've been able to capture and use. There's a thing like Pareto-based targeted sampling to go and see what else can we know a little bit about the unknown. The motto we live by is, you never model what you know. You always take on board the factual data. You will repeat this process multiple times until you've got a knowledge about the industry or the commodities or the national country that you're doing modeling for. So let's say we get to this point of data saturation, whereby almost of diminishing returns if you were to spend more and more investment on this. This becomes a hybrid input data sourcing. So we follow all the capturing we can to understand everything that we possibly can know about freight on a disaggregated level. The point is it has to be disaggregated, be able to have a disaggregated output. Then you do things like using populations or using inputs to have a disaggregated of supply and demand. I've touched on it a little bit now. Up until this point is purely just now data. This is just capturing, understanding, disaggregating, populating. This is the kind of office like you'd be working on a computer yourself. You would be the inputter. Then we'd use things like gravity modeling. This is mathematical techniques. You can use software that does it. And you can now start creating freight flows for the unknown. This is the step 3 on modeling, which I'll touch on a few more slides. I've got a different alternative to try and explain these. And then you have outputs, which become the disaggregated national freight demand modeling. That is the outputs of knowing all those origin, destination, etc. At this specific point over here is where you do things like adding on forecasts. If you've got a disaggregated supply and demand, to go and say, how will these points of production and points of consumption and demand, how will that change over time? If you know things like how people are moving, let's say, collating towards the city or out of the city, if you know sort of production areas of agriculture, you can start making analysis and estimates of future volumes. Now this sort of model becomes a lot more robust. So another slide of doing exactly the same and a slightly different output. So I've explained to you how we've got a process of capturing data, and it goes from data, disaggregation, freight modeling, outputs. Now I've tried it in a different way to tell you, we start by selling all of this data, and there's many uses of this, or inputs of this. You could be using a national input-output table, which tells you the interrelationships between economies and subsectors on a national level. You can have macroeconomic data sets like GDP, which also can tell you even disaggregated aside. You can then look at things like provincial. Here in South Africa, I live in Cape Town, which is part of the Western Cape. The Western Cape puts out some great information specifically that targets the agricultural sector of the Western Cape. So there's a lot of information. And then on a geographical area, we look at things like import-export data at a port or a border post, which is generally known. We look at things like shipping data for containers, and so this has got bulk and containers, but specifically the containers can give us a lot more detail. And we then look at things of actual flow data. So as I said again, you never model what is known. You can often find what is moved on railways. Railways records every single movement because every single movement results in an income for them. Somebody's being charged. So you can find factual data on rail, on waterways, on pipelines, and on conveyor belts. This then becomes a big pool of data of what you do know. So what you have is when you get to this point of the supply and demand disaggregated table. So in my previous slide, when we get into this step, before going from a disaggregated supply and demand model, tables, to actually doing the modeling, we first subtract. So you see it says total supply and demand less the origin and destination of all actual flows. Remove everything that is known. Result with only the amount of freight on a disaggregated supply demand point level of what that freight is before doing freight modeling to determine origins and destinations to actually create flows. We do this by using decay factors, and I'll touch on that now. A decay factor is, in a simple sentence, the relativity between volume and distance. So how important is the distance to the freight? If you've got a very expensive commodity that is specifically like a good brand or a quality product, then generally it can incur a much higher distance traveled and a much higher transport cost relative to what the product is. Whereas if you're moving a very generic product, you're moving sand, aggregate, you're moving things like sugarcane, barley, wheat, things that can be replaced. Now that distance becomes far more crucial in having that minimized because you can actually obtain those same products somewhere else. So we only do gravity modeling on the unknown. You model what you don't know, and then you stitch back by saying, once you take the unknown, these model flows, then you add all the origins and destinations of all the actual flows to give you this output. So this part here gets quite tricky. So to tell you again, this is just showing you relative examples of different decay factors for gravity modeling. So if you go and see a power function, so these black lines over here are showing you a mathematical power function, and these blue lines over here are showing you the mathematical function of an exponential function. What you might see for these three blue lines is that at different distance intervals, they reach zero. So what this means is for all of these examples, it's going to be a commodity that does have a cutout point whereby at a certain distance, it's no longer viable or desired, or for many reasons, it's not going to travel further than that. So something like sugarcane, you can obtain it somewhere else or closer or easier. There's not going to have a distance. And if you take a commodity that might have a power function like this black line over here, this is a good example of something like motor vehicles. Even if you live right next to the factory that is producing Ford vehicles, if you want to buy a Mercedes-Benz or a BMW, you're still going to need to get that Mercedes-Benz or BMW from the factory location where those Mercedes and BMWs are produced. So then what happens is you are not really influenced by your distance to a manufacturing plant. You have a brand preference. So vehicles have very little influence on distance. The buying behavior is what they specifically want. Now, everywhere between, so this might be a product, this dotted line, like sugarcane, whereby sugarcane is so low value, it goes straight from an agricultural point, goes straight to a milling location. That's going to be about 17 to 20 kilometers average distance. And every single possible function line could be between here, with different slopes of curves, and between ones that never reach zero and ones that do reach zero. Even if I was to go and take a power function that was to drop down here, a power function never reaches zero, but an exponential function does reach to zero. So it depends on the type of freight that we're looking at to go and model. Now, how do you determine these average travel distance? The first one is to understand, does something cut out at zero? So you can see, is it more suitable for a power or an exponential function? And then we do things like saying, okay, let's go and try and model the freight from the minimum and maximum. So you can see, if you were to make all supply goods go to the demand at the closest location, you can do the minimum or you can do the maximum. Now you can start to go and see a range of what is possible. Then from this range, you can start influencing it by intelligence or by studies, and you can start improving on these sort of flows. I'm going to skip some of these slides due to time. I've told you about all those sort of productions, but some steps to follow is to collect data, evaluate the data, collection, sanity, populate. And this is the important one of this slide, is once you've done this model, to every time iteratively improve with new data. I'll skip some of these slides, they're just building up. I've told you between known flows and between known data and model data. So I tell everybody it's sort of like a puzzle to try and understand the whole scenario of understanding freight flows. So here's a representation showing you supply and demand on the left and the right. What we're trying to do for a model is we try and say we need to have an output approach from day one. Instead of building up like a wheel, then building a sort of a subframe and then a car, we try and say, let's go and build a skateboard model first, and then improve with a scooter, and then with a bicycle, and then with a motorbike, and then a car. For all of these countries, we've used different data sources. But what is important is some of these, like agricultural statistics, trade data, mining data, and populations, this is available for almost every single country. This enables us to go and produce a high-level model from the beginning. This is a representation of agricultural data. You can go and find every single pixel goes and represents what is being produced on an agricultural level for these countries. So now this data, if I translate it into being productions, I can go and see volumes for every commodity, for every district here in South Sudan. So you'll see there is all agriculture, there's grain, sorghum, there's maize, cassava, groundnuts, rice, milk. This allows us to understand things. So once we've got all the points of production, we're trying to say, how do we make this in terms of gravity modeling? How do we even do things like look at distances? So what we do is we look and say, where is the center point of each district? What's their connectivity to existing infrastructure and road and rail networks? Then you'll see a place like this little dot over here. It's center of a district, but it's not connected. So then we start going one by one to go and say, but let's move all of these red dots to the new blue dots. So we can start saying that the blue dot is actually the economic activity and where there is connectivity towards networks. Now you get a simplified network. Now you can determine distances or transport times between each of these and use that for gravity modeling to determine the interaction between any pair of these two blue dots. So the visualization to say, taken inputs of supply, taken out inputs of demand, such as where populations are or where industry is, use gravity modeling to create freight flows that look like this on a sort of a network. So that's the sort of outcome. And this has been done for every single commodity for all countries. It's the same methodology. Here is 6 examples of supply, and that's how they result. You can see how visually different each and every commodity results for their flow pattern. Now, if you were to go and look at all agriculture, it becomes very difficult to model. But milk is such a different commodity to say maize or to say rice or even groundnuts, that the value here is doing disaggregated modeling. You could always add the commodities back. You could always be able to go and show a view for agriculture, but to start from the ground up from details. So to tell you one slide, there's many trip ups if you use different data sources. Here's an example using FAO agricultural data versus MapSpam data. You'll see that this north region is very different. So I just want to give a warning for anybody that does freight modeling to never be too reliant on one data source. They can have a very, very different result by being tripped up. The whole model can be perfect, but there must be some sort of checks on the data inputs. I'll skip some of these, but just to tell you, the same methodology was done for India, where there's 7 million unique flows. I think out of my head, it's about 4 billion tons of freight was done in India. The same methodology was followed for Mongolia, which has only got 67 million tons. But then again, looking here, you can see the supply and demand for agriculture, mining, manufacturing, the same methodology giving out results of a flow pattern on a network. So Mongolia's got 67.4 million tons, but a very, very, very wide, large landmass. Then a country like Uzbekistan, not that much of a land mass, but 195 million tons. So my last slide is to tell you that the value of disaggregated freight modeling definitely exists. Emerging economies do not have to be stuck by theoretical models or off-the-shelf software. There are forms of freight modeling like I've shown you here. So this is still showing that there's value and importance of having standardized outputs. It can be difficult in some countries, but we've proved that it can be done. So what we say is, despite all these challenges, there's been evidence that disaggregated gravity modeling with these dynamic decay factors for each commodity has been successfully delivered for each economy. So I believe that this can be done for, touch wood, any country that exists on the planet, that this can be enhanced. That's what I wanted to tell you today, and you can ask me any questions at all about this.
Thank you very much, Zane. I really appreciate it. There's an echo. Why is there suddenly an echo on the line?
I don't hear it.
Just ask everybody to mute themselves.
If everybody mutes, then an echo. I wonder, yeah, I'm sure there's lots of questions, Zane. I wanted to maybe what I must do is very, very quickly just show how we apply this. So one of the things that we do in a case like this, David, Phil, is a lot of people think that this is just an academic exercise, but all of these things assist us because many of these countries now have to create infrastructure. And what we're trying to do, a lot of infrastructure investment there compared to Europe and the first world, we're trying to direct that infrastructure to sustainable solutions, and also in terms of the policy, I would call it the policy things that needs to nudge freight in the right direction, if I can call it that. So maybe I'll just quickly go through some examples of how this is actually used. I just want to check whether my screen is actually being shared, because it seems everybody can see my screen. You can see it now, Zane. So yeah, I'm just going to quickly run through some examples because I'm going to leave some time for questions at the end.
Use more. Sorry.
Yeah. That's fine, not a problem. That's very interesting. So I'm going to look at South Africa, Uzbekistan, connectivity and freight villages in India, and then sustainable herding in Mongolia, and some of the regional value chains in the Horn of Africa. For South Africa, we then do this. We forecast it up to the year 2050. This is about, Zane, if I remember correctly, about an 80 gig database of all of those things that you talked about. And one of the examples, for instance, one of the things that they found, South Africa is about the size of France and Germany. But where France and Germany has got a GDP of 6 trillion, South Africa has got a GDP of 0.35 trillion. There's massive, massive challenges because of that. If you think about ton kilometers as an input into the economy, you can measure things like ton kilometer productivity. And South Africa and India has got some of the lowest in the world, which makes it very transport intensive. And transport intensity towards the same GDP just means a huge amount of unnecessary emissions, if I can call it that. In South Africa, we've just written the first road to rail strategy for South Africa for the presidency, where we identify the various gaps in terms of what modal shift could happen. The modal shift opportunities for South Africa is just massive compared to Europe. But I'll just take it, compared to Europe specifically. I'll just take one very, very simple example. If you look at palletized cargo in South Africa and you look at the various flows, we can identify flow between each one of the 400 districts and import and export locations. And we can identify what we're definitely sure about is rail friendly. This is distances of this corridor over here, massive distances of 700 kilometers, and this corridor over here, 1,400 kilometers, which is the distance from Rotterdam to the other side of Warsaw. Each one of them got about 40 million tons of freight. And then we went and we said, all of those things are on road. And we then said to ourselves, if that's all on road, why don't we have domestic intermodal solutions in South Africa? It's quite common in Europe. It's quite common in America. You need to show people in South Africa this graph that looks at ISO, that's import containers in America. The growth of that versus the growth of the GDP of the USA. And this is domestic containers. In fact, today, if you find a container in America, 1 out of 2 containers probably did not cross a quay wall. Massive drive of rail freight, good solutions, so we don't have that in South Africa. So we were able to say, if you go from a manufacturer to a distribution center, then to a DC, often 1,400 kilometers away, and then to a retailer, most of that freight, in terms of palletized freight, is on the road. If we can start creating natural logistics hubs on both sides, because we have the model that Zane talks about, we can go and say, if you move from that to that, you can actually work out exactly how much volume should be targeted, and it's more friendly and useful for rail, even if you just take the 2 biggest corridors. What Zane touched upon when he talked about cost, our cost model includes the actual internal cost of all of those flows for every flow, but it also includes external cost, 6 externalities is included, like congestion, policing, accidents, etc. Most importantly, emissions is also included. So for each one of these solutions that we propose, in terms of the type of infrastructure that should be inserted in this economies, we can then calculate what the emission savings would be. In this case, 400,000 tons doesn't sound like a lot for our economy. That's quite a bit. And we can do that for any economy if you have external costs added to your cost model, specifically like that. If you take a place like Uzbekistan, for instance, Zain has shown the slide, about 195 million tons of freight flows in Uzbekistan. Uzbekistan is right in the middle of Central Asia. A huge amount of freight actually just crosses the country. So we started looking at things like freight villages, collection points, things like that within Uzbekistan. Also, because Uzbekistan is one of the only 2 double landlocked countries in the world, the other one being Liechtenstein. And because of being double landlocked and it doesn't have a maritime port, there's a huge amount of other challenges in terms of road freight for Uzbekistan. We've interviewed people in Tashkent, in Uzbekistan, that has freight flows of 6,000 kilometers on the road. They have clients. Some of the people over here have got clients in Eastern Europe. And many of that is on the road. And that's just clearly untenable. It clearly should not be like that. And the damage because of that is just huge. Also the damage in terms of sustainability, in terms of emissions, in terms of carbonization, carbon in the economy and carbon in logistics as such. In fact, if you look at it, in terms of Uzbekistan, if you look at every freight movement that starts and ends in Uzbekistan, both domestic and import and export, you find that post-border freight in Uzbekistan is actually nearly as much as freight within Uzbekistan. And if you compare this year, that 80 billion ton kilometers to the 60 billion ton kilometers with a place like South Africa and many other countries, except if you look at regional situations like Europe, obviously, it's not structured like that, America, etc. And the fact that maritime nations benefit. We often target shipping, global shipping, which is correct, and it should be done for decarbonization and things like that. But it's a highly organized industry, highly organized, whereas land freight that crosses borders is not organized. It causes huge problems. It causes stoppages at borders, etc. Usually smaller freight operators that does not understand or not able to find return loads, etc. So land borders are highly inefficient and carbon intensive. So what we try to do through our modeling is to find ways of explaining to people, for instance, to develop things like one-stop border posts, quicker ways of passing borders, etc., etc. Once again, having the evidence of every flow makes it easier for us to work out the cost-benefit analysis, both in terms of cost and in terms of emissions for each one of those. If we look at a place like India, for instance, a lot of work that we've done in EVR India, Zain has referred to the 7 million unique flows that we've got. We're able to calculate, Zain, you're right, 4.6 billion tons of freight, 3.1 trillion ton kilometers, huge and long distances, with a very high carbon intensity for the economy. And interestingly, even though rail transport is much cheaper in India, there is not even an issue. The rail is just off road, but the problem there is that there's not enough capacity. There's a huge capacity gap in terms of freight transport. India, I think about every person in India spends about 1,000 kilometers per annum on rail. Passengers gets priority and it's also subsidized by freight in India. So there was a huge drive to develop dedicated freight corridors. After we've developed this model, we concentrated on the Eastern Corridor, one of the most densely populated areas in the world. We look at all the freight flows over there, the warehouses, where they're situated, where the points of supply and demand is, and then a $4 billion investment that the World Bank has made into the Eastern dedicated freight corridor. So what India is doing is building freight corridors on a rail that's dedicated to freight and does not carry passengers to solve the problems that I talked about. Once again, looking at this, we're looking at a place called Dankuni. The freight corridor has been designed to end in Dankuni. Dankuni, unfortunately, is not in the city center and it's not close to the port. It's outside of the port. And this is a hugely congested area, more or less no solution here to get from Dankuni to the center of the city, where about 20,000 trucks try to enter the city every day. They're not allowed to do that between 8 o'clock in the morning and midnight. I've never seen such congestion in my life that I've seen in Kolkata. The problem here is if you said, if you can create a logistics hub or a freight village or something like that outside of the city, once again, because we have this by here as Halia Port, because of this, we were able to calculate the exact type of freight that would move if you do that. So if you look at it, we said already we bank that the new rail corridor will save the economy of India $1 billion per annum. But if we can create that high density link that I've just spoken about, there's more savings. If we can have a high density link towards the port, there's more savings. If we do this efficiently, strangely enough, a lot of freight in the hinterland of Kolkata goes all the way towards Mumbai, which is further away because of the inefficiency of Kolkata port. But if we can do that, we can create and attract new rail freight. We can attract new road freight. And altogether, we've calculated that only 38% of the current dedicated freight corridor is utilized, or I would say is achieved by what we currently have. But if we were able to create a high density link, we can actually save the economy of India another $2 billion US dollars per annum, with all the concomitant sustainability and decarbonization benefits that goes with that. That same corridor, if you look at the city of Varanasi in the middle of the corridor, which is on the Waterway 1, what we've done there is that they've developed a terminal here in Varanasi for waterways, so Waterway 1, and we've calculated, and they have at that stage designed the Varanasi port, inland port, to carry 0.5 million tons. But we said if we can change this into a freight village, the potential is actually 30 million tons. To give an idea, about 60 million tons of freight passes through Varanasi every year. And this is if you have a hinterland view and put here not only but an extended gate for the Kolkata port, you float most of the freight up to the river and then take it up by the rail corridor, the dedicated freight corridor. And once again, because Zane has got the data that we spoke about, we could calculate exactly how many tons could be targeted. Now, a freight village is a wonderful concept that works well in Europe. It's not that well known in the developing world. It shortens the distances between supply and demand and has a huge impact in having less freight intensity for the same relative output. We've done the same for Mongolia. We've developed this model that Zane has shown. Once again, here, Mongolia is highly dependent on freight outside of its border. But here, just give an example, we've developed ideas of how we could improve the future of Mongolia in terms of its GDP and freight intensity. So this is GDP growth versus certain interventions into the economy. And this is the lowering of freight intensity. And through this, we could target meat and DRI, which is directly reduced iron, and say this is probably the best options of making Mongolia a better place. We chose meat because there's 400,000 herders in Mongolia that has a tough life, and we think if we can improve their life, it makes a difference. Now, this is very interesting in terms of decarbonization. The national herd of Mongolia has doubled over the last decade for lots of reasons, but mostly because of logistics, because of poor logistics, because of no cold chain, because of the way in which animals are slaughtered and transported, the diseases that it causes, etc. Because the output from this is not additional exports. The output from this is not more people eating meat. The population stayed about the same. It's waste. And it's waste because of while the animal is live, there's a lot of diseases and stuff like that. The carcass perish once it's been quartered and butchered, poor abattoir practices, and the way in which this meat is traded. So we've proposed consolidated clusters right through the country of Mongolia. We spoke to the World Bank yesterday. We think the loan for this will be approved. We hope so, to start developing this system. And if you have this clustered flow of meat with mobile abattoirs that picks up the meat at various points within the economy, if you don't break the cold chain, if you have cold chain hubs, if you invest in just targeted roads through this, we say what you can do is you can have massive growth, cost savings, and very interestingly, emissions relative to output in terms of freight intensity is reduced. But also interesting, if you look at it, has a significant higher yield from the national herd, reducing the manure-induced carbon release per ton of meat produced, which can have a huge effect if you think about 70 million animals in the country. We've done the same for the Horn of Africa. Zane has shown this picture. Here, for instance, we looked at something like grain sorghum in value and production. In South Sudan, they produce about 300 to 400 hectares, up to 600 kilograms per hectare, which is sometimes between 5 to 9 times lower than the world average should be in terms of this. We've calculated what type of roads can be inserted, where they could be inserted to have sustainable development and to reduce waste. Now, if you think about it in terms of milk, if you think about it in terms of milk, we looked at both grain sorghum and milk. South Sudan uses 3 times the comparative average of milk than the rest of the world, once again because of waste. Once again, we say we can reduce carbon intensity and transport intensity by having inserted infrastructure in the right place, and interestingly enough, moving away from roads as well, using the waterway, the Nile, and from the Nile up to a place here called Kosti, and from Kosti there's a railway line to Port Sudan. And we can move away from road, but they will have to design something in terms of the waterway that can support this in terms of nitrogen and other inputs, and then in terms of machinery as well. And then the outputs, also one of the other things is reducing the reliance on food aid right through the world, which strangely enough, if you think about it, if you don't have food aid but you produce your own food, you also decrease the carbon intensity of the use of food. And that's what we're trying to do, and then we will also export some of them. This process could eliminate substantial waste, and it increased the calorific output per kilogram of carbon of calories per kilogram of carbon emissions. But here we have to have a regional value chain approach, because this involves both North Sudan, and South Sudan, and doing it like that. Yes, this is more or less the methodology that we follow, and how we use it in terms of sustainable transport around the world.